Hi everybody. In this section 13.3 we want to talk about randomized complete block design. So the objectives here will be to conduct an analysis of variance on randomized complete block design, so we are still going to be doing our ANOVA test, and then perform the Tukey test on that we talked about in the last section 13.2. So in a completely randomized design, the researcher manipulates a single factor and fixes it at 2 or more levels, and then randomly assigns experimental units to a treatment. This is not always sufficient because the researcher may be aware of additional factors that cannot be fixed at a single level throughout the experiment. So the randomized block design is an experimental design that captures more information and therefore reduces experimental error. So in other words, another way of saying the same thing is a block is a method for controlling experimental error, and blocks should form a homogeneous group. For example, if age is thought to explain some of the variability in the response variable, we can remove age from the experimental error by forming blocks of experimental units of the same age. So gender would be another common block, for example. Word of caution here. When we do use blocks, we're not interested in determining whether the block is significant. We only want to remove experimental error to reduce the mean square error. So our first objective here then will be to conduct an ANOVA test on the randomized complete block design. So a couple of requirements here that have to be met for analyzing data from a randomized complete block design are that the response variable for each of the K populations must be normally distributed, and the response variable for each of the K populations has the same variance. That is, each treatment group has population variance of sigma squared. So let's look at an example here. So let's say that a rice farmer is interested in the effect of 4 different fertilizers on fruiting period. He randomly selects 4 rows from his field and that have been planted with the same seed, and divides each row into 4 segments. The fertilizers are then randomly assigned to 4 segments, and assume that the environmental conditions are the same for each of the 4 rows. The data given in the next slide represents the fruiting period in days for each row/fertilizer combination. Is there sufficient evidence to conclude that the fruiting period for the 4 fertilizers differs at the 0.05 level of significance? So here's our table. So we basically wish to test whether the means for all these fertilizers are the same. So either the means will be the same, or at least one mean is different. So we first have to verify the requirements for the test, normality and things like that. And again, I'm not necessarily going to show you the normal probability plots in this case, but a lot of times, again, it will say, for example, on the exams, you can assume that conditions are met. But so then step 2, we want to compute S sub 1, S sub 2 for each one of these things, the standard deviations for each one. Since the largest standard deviation is not more than twice the smallest standard deviation, right, the assumption of equal variance is not violated. So again, those are our 2 conditions, normality and the conditions for the standard deviations. And we aren't going to do the computations here by hand. We'll just use an output from, say, for example, Minitab or some other statistical software. So again, you can see the some of the calculations here if you want. So here's our F value, and then here's the P value. And so the P value is quite low, so in this case. So since the P value is less than 0.001, it will certainly be less than 0.05, which is our alpha level. And we can conclude that there is a difference in fruiting period for the 4 fertilizers, right? Now we are not interested in testing whether the fruiting periods among the blocks are equal, so keep that in mind. So now that we've determined that at least one of them is different, then we need to check and see which ones are different. So to do that, we will go back to what we talked about in 13.2 and use Tukey's test. So once the null hypothesis is rejected, right, we can proceed to determine which one is different. So the steps are pretty much identical for those comparing means in a one-way ANOVA. Right, remember the critical value is this, and again you want to use the family-wise error rate of alpha with the row, again this is the number of rows minus 1 times the number of columns minus 1. That'll equal the degrees of freedom, and k is the number of means being tested. So let's use Tukey's test to determine which pairwise means differ for data presented in example 2. And again, we'll use Minitab as an output in this case. And a lot of times, if I do give you a problem like this, I will give you the Minitab output just because calculating these things by hand is, although it's possible, it is quite lengthy and tedious. So again, you might want to sort of just familiarize yourself with these outputs a little bit. So here's the values here. And so here are the adjusted p-values here. So so if that gives you guys an idea of what to do for that section, if you guys have questions about anything else, just let me know. But you can see the p-values here are highlighted in red. So that's all we're covering in section or chapter 3. The next section will be two-way analysis of variance, but we're not really going to be covering that section. If you want to read it, you certainly can, but that will not be on the exam. So, all right. Hope that makes sense. So the next thing we'll look at is chapter 14, and the only thing you'll really be responsible for in chapter 14 is 14.1. So hope that makes sense. If you guys have questions about anything else, just let me know.